Hi everyone. So let's do one more problem where we have this BVP and we have to find its eigenvalues and eigenfunctions. We'll start with case 1 where lambda is less than 0 and we're going to define a constant mu squared that is equal to negative lambda. So we can conclude that mu squared is greater than 0. Since lambda is less than 0. And let's go ahead and solve our problem. Our ODE becomes y double prime minus mu squared y is equal to 0. And if we write down our characteristic equation, we have r squared minus mu squared is equal to 0. Therefore, r is equal to plus or minus mu's. So, if we write down our general solution, let's write down our general solution, but let's do so in terms of sinh and cosh for convenience. In the last video, I explained a little bit why we do that. This video, I'm just going to go ahead and do that. So C1 cosh of mu x plus C2 sinh of mu x. And let's apply our boundary conditions. Our left boundary condition says that if y is equal to 0, if y of 0 is equal to 0. So if x is equal to 0, y is equal to 0. C1 cosine of 0 plus C2 sine of 0 is equal to 0. And since we know that sine of 0 is equal to 0, this term vanishes, and cosine of 0 is equal to 1. So we have C1 is equal to 0. What about our right boundary condition? Well, our right boundary condition says that we need to differentiate our general solution because it's y prime of pi is equal to 0. So if we differentiate this, first recall that the derivative of cosh of x is sinh of x, and that the derivative of sinh of x is equal to cosh of x. You could differentiate this on your own to see that it actually works, but these are the derivatives of cosh and sinh. So when we differentiate our general solution, we're going to get mu c1 sinh of mu x, and we get this factor of mu here because of the chain rule when we differentiate this inner function, plus mu c2 cosh of mu x. And the same reason we get this mu here, because when we differentiate this inner function, we have a factor of mu here. So this is y prime. Y prime of pi is c1, it's actually mu c1 sinh of mu pi plus mu c2 cosh of mu pi, that is equal to 0. So since we know that c1 is equal to 0, we know that this term right here vanishes. So this term is equal to 0. And what about this part right here? Well, we need to consider the graph of cosh of x. Let's consider the graph of cosh of x. So the graph of cosh of x, sorry for my bad drawing, but graph of cosh of x will look something like this. It is never 0. For any value of x, it's never 0. So we know that this term right here, cosh of mu pi, that is not equal to 0. Furthermore, we know that mu squared is greater than 0, so mu is greater than 0. Since mu is greater than 0, it is not equal to 0. And since the only thing that makes the equality true is that C2 is equal to 0, then we need C2 to be 0, because mu is not 0 and cosh of mu pi is not 0. So in order for this equality to hold, we need C2 to be 0. And since we have C1 is equal to C2 that's equal to 0, we have a trivial solution. And remember that when we have a trivial solution, there are no eigenvalues in this case. So therefore, no eigenvalues for lambda is less than 0. This is our conclusion. We needed to go through this case. Now let's consider case number 2. So let's consider case number 2. We have that mu is equal to 0. If we have that mu is equal to 0, then our ODE becomes y double prime is equal to 0. From here, we can write our characteristic equation. R squared is equal to 0. And so the solution of the characteristic equation is 0, like a repeated root of 0. So we have 0 and 0. If we write out our general solution, y of x, then we have c1x plus c2. And the reason for that, I kind of explained it in the last video, but since we have since our full solution would be c1 e to the rt plus c2 So our full solution, like just to remind you, when we have a repeated root, our full solution would be c1x e to the rx plus c2 e to the rx. This would be our full solution, but since r is equal to 0, then this term is going to be equal to 1, this term is going to be equal to 1, so this is our actual solution. So just a little heads up, this is our solution, and when we apply our boundary conditions, our left boundary condition says that y of 0 is equal to 0. So therefore, y of 0 is equal to c1 times 0 plus c2 from here. So c1 times 0 is 0, so we have c2 is equal to 0. So here, this is what we found when in the left boundary condition. What about the right boundary condition? Our right boundary condition, we need to differentiate this general solution that we got. So when we take its derivative, make this a little bit clearer. When we take its derivative, we're just going to get c1. Y prime of x is a constant, c1. So y prime of pi is equal to c1, that's equal to 0. So c1 is equal to 0. In this case, since c1 is equal to 0 and c2 is equal to 0, we get the same conclusion. c1 is equal to c2, is equal to 0, implies we have a trivial solution. So therefore, no eigenvalues for lambda is equal to 0. This is the conclusion we have. we have one more case to consider, that is when lambda is greater than 0, and let's go ahead and do that now. So, case 3, when lambda is greater than 0. When lambda is greater than 0, we're going to define another constant, mu squared. It's equal to lambda, where mu squared is greater than 0. We're doing this just for convenience, so we don't have to keep writing square roots in our calculations. But this is going to make things a little bit easier when we write things out. So let's define this constant mu. Then our ODE becomes y double prime plus mu squared is equal to 0, and our characteristic equation is r squared plus mu squared is equal to 0. So from here, if we solve our characteristic equation, we have that r is equal to plus or minus mu I, where I is the imaginary number. If we write down our solution, the general solution to this solution, we have that y of x is equal to c1 cosine of mu of x plus c2 sine of mu of x. And this is just the solution when we have pure imaginaries in our characteristic equation. This is just using the relationship that we know. So this is what we have for our general solution. Imposing our boundary conditions, we have that our left boundary condition y of 0 is equal to 0. So c1 cosine of 0 plus c2 sine of 0 is equal to 0. Since sine of 0 is 0, this term vanishes. Cosine of 0, this is equal to 1. So c1 is equal to 0. Alright? What about our right boundary condition? Our right boundary condition says that, first we need to differentiate our general solution, because our right boundary condition is involves the derivative. It has y prime of pi is equal to 0. So if we differentiate our general solution, y prime of x is equal to negative mu c1 cosine, sine of mu x plus mu c2 cosine of mu x. Again, I'm just differentiating this using the chain rule here. We get negative mu, and here we just get mu as a factor, just by using chain rule. So if we impose our right boundary condition, y prime of pi is equal to negative mu c1 sine of mu pi plus mu c2 cosine of mu pi is equal to 0. And here we saw that c1 is equal to 0, so we're going to use this right here. Since c1 is equal to 0, then this term vanishes, is equal to 0. And now here comes the fun part. We have to analyze this. Since mu has to be greater than 0, because mu squared is greater than 0, this term right here won't be 0. So mu is always greater than 0. What about cosine of mu pi? What about cosine of mu pi? Well, if we want non-trivial solutions, we need c2 different than 0. So let me write this down. So for non-trivial solutions, which is what we want, we need C2 is different than 0, and, which is the important part, cosine of mu pi is equal to 0. So this is the important part. Cosine of mu pi is equal to 0 because we want this term to be 0 and this term to be different than 0. It all has to satisfy this equality. You kind of have to look at it and you have to say, what cannot be equal to 0? Mu cannot be equal to 0 because we've defined it as positive. C2, that can't be equal to 0 because we need non-trivial solutions. And cosine of mu pi can't be 0, so we're kind of forcing it. We need cosine of mu pi to be 0 in order to have non-trivial solutions. Okay? That's the only thing that can be 0. So let me erase this part of the board. The only thing that I'm going to keep is the fact that C1 is equal to 0, because when we write down our eigenfunction, that's going to be important. So let me erase this part of the board. Alright, so now let's consider cosine of mu pi is equal to 0. Well, if this is equal to 0, then we need mu pi to be pi over 2, 3 pi over 2, 5 pi over 2. We kind of get this pattern. And if you can't kind of visualize it, I always like to think about a trigonometric circle. I usually see cosine in this axis right here and sine in this axis right here. Sine x. This is 1, this is -1, and this is 0. If this is unfamiliar to you, I don't know if it's good. I don't want to confuse you, but this is the way that I think of it. It's very useful to me. The places that cosine of x vanishes is in these 2 points right here. And if we think about it, if all of these terms are pi over 2, 90 degrees, then this is pi over 2, this is pi over 2, this is pi over 2. So when we add this all up, this is 3 pi over 2. And we can keep going in circle. This is 5 pi, can be pi over 2, 5 pi over 2. This can be 3 pi over 2, 7 pi over 2. It's kind of like a pattern. But if you didn't learn like this, I don't want to confuse you. I'm just showing you the way that I usually think of it. But here we have this nice little pattern for us. We can divide by pi on both sides to find the pattern for mu. So mu is 1/2, 3/2, 5/2, and blah, blah, blah. And what we can see is that we have odd numbers in the top and 2's in the bottom. So we can write this as 2n minus 1 over 2, where n is an integer. Alright, so this is our expression for mu of n. Once we're here, it's pretty easy to find our eigenvalues and eigenfunctions. So our eigenvalues, let me erase this part again because I keep running out of space, or I think that I'm running out of space. So I'm going to write the solution to the whole problem here. So the eigenvalues, mu is, lambda is equal to mu squared, which is equal to 2n minus 1 over 2, all of that squared. So that is our eigenvalues, mu of lambda of n. What about our eigenfunctions? Our eigenfunction, well, we're just going to use our general solution, and we're going to see that C1 is equal to 0, so this term vanishes in our general solution. We're just going to consider this part right here, C2 sine of mu x. So our eigenfunction yn of x is equal to C2 sine of mu. Remember that this is mu squared, so mu is just 2n minus 1 over 2. So this is our eigenfunctions, or you can simply write it as sine of 2n minus 1 over 2 times x. You don't need this constant right here. But here you have it. This right here is our eigenvalues for all values of n, and this is our corresponding eigenfunction. So I apologize that the videos are getting a little bit too long, but just the process itself is long. So we need to consider the 3 different cases when we're finding these eigenvalues and eigenfunctions. So I hope this helps, and I'll see you next time in section 10.2. Bye.